Welcome to BISCO Tutorials. You can find the corresponding files to download from the link mentioned in the description of the video. In this first tutorial, you will learn a few basic tools and understand the interface of BISCO. For this first tutorial, we will use the simple 2D thermal problem outlined as a validation case in Annex C of the standard ISO 10211. We have a square with a dimension of 2.8 meters with a surface temperature of 20 degrees on top, and a surface temperature of 0 degrees on the other three sides. Once you download the corresponding files, you have a BMP file, which is a bitmap file, and BSC file, which is a BISCO file. Now open BISCO application, from File menu choose Open. Choose the BISCO file from the file location. Upon opening, you notice for Windows, bitmap, measures, colors and border U values. Each pixel is read from the bitmap and the dimensions of these pixels, or geometry, can be altered from the measure window. At BISCO we define a material, or boundary condition using a color, which is assigned to each pixel. We can input the color from the default Physibel color database or customize the color to alter the properties of material, or boundary conditions. You can use scroll wheel to zoom. If you click on any pixel on the bitmap window, the corresponding color assigned is highlighted at Color window, and geometric dimensions are highlighted at the Measures window. Since the square geometry considered for this exercise is symmetric, we can model a half geometry, and consider adiabatic conditions along the symmetric axis. Here on top, we have 20 degrees and other two sides we have a boundary condition with 0 degrees. Inside the geometry, we have two materials green and orange with the same conductivity 1. We could have taken a single color to fill the entire geometry, but we considered two colors to have a grid matrix formed at the graphic result with squares with a side 35 centimeters. The boundary condition on top is defined with color 5 cyan, with a temperature of 20 degrees, and a very high surface heat coefficient to have almost no resistance. Similarly for yellow color 7 we have temperature 0. Here boundary conditions are defined using type BC simple and materials under type material. We will talk about these later under the BISCO colors tutorial. The thickness of the boundary condition doesn't affect the result. If you zoom in, you can see several pixels. Only the pixels adjoining the material are used for the calculation. The remaining pixels are just to visually identify the layer of boundary condition. Since all pixels must be defined, at the corner we give adiabatic conditions with gray color. Here surface coefficient is 0, which means heat cannot pass through these pixels. On the right-hand side, we haven't given any boundary conditions, so BISCO assumes that this is an adiabatic edge. At the measure window, you can alter the dimensions of the geometry. Here you see the width and height of each pixel, and they are linked to each other to maintain the geometric shape. Suppose you change the pixel width to 0.002 meters, then you notice pixel height also updates automatically. For color 5, there are 140 pixels in total along the width and 10 pixels along the height. Since the width of each pixel is 0.002 meters, total width of color 5 is 140 multiplied by 0.002, which is 0.28 meters. Similarly, you see the total height of pixels with color 5 as 0.02 meters. You can also see the width of the green color as 0.28 meters for 140 pixels in total and split into 16 zones. We now know that our total width of the geometry should be 1.4 meters. In that case, we input to 1.4 meters to the width of green or orange color. You notice that pixel height and width changes to update with the current dimension, and all other the corresponding dimensions for the remaining colors also change. So at the measure window, you have the freedom to scale at the level of pixel or at the level of geometry. We need to triangulate the grid to perform analysis. Here we say that one side of the triangle is 5 pixels. This is a coarse mesh. But we can first perform analysis with these settings to visualize the result. Click on the magic wand icon to calculate the system. Choose Yes for recalculate triangulation. Click on Graphic Output to visualize the result. Here choose Fill Temperatures and Triangulation Mesh to view the temperature gradient, and Mesh used to perform analysis. You can now see the heat transfer through the geometry. On the left top corner, we notice that due to a large temperature variation from 20 degrees on one side to 0 degrees on the other side, there is a glitch caused by this coarse analysis mesh. We will now try to refine it. You can close the graphic output window. Using Fill icon, select the orange color and click on all the green segments except the left corner segment. So now all the geometry is filled with orange except the left corner segment, as we need to refine it. Now at the Measures window, reduce the triangulation of the green color to 1. So in the area of green, we have a finer mesh, and we'll leave the orange segment as it is. In this way we can refine the mesh by not making file size too heavy. If you input the triangulation value at the level of pixel, all the triangles for all colors would be scaled. Now click on Calculate System, and choose Yes to recalculate triangulation. Now if you turn on the view of the triangulation mesh you observe a finer mesh at the left corner. You can now close the graphic output. Thank you for watching, see you in the next video.